BTEC Applied Science for AAQ, and this video is about covalent bonding. The adventure continues. So, covalent bonding, what's that then, Dave? Well, I'll tell you. So, two chlorine atoms, and each one has got 7 electrons in its outer shell. And each one would very, very much like to have 8 electrons. So what happens is that they get together and they share a pair of electrons. And if they do that, then you have a covalent bond. And each one gets at least a share of a full outer shell. Now, here's a molecule that hopefully you recognize, 2 hydrogens and an oxygen. And we have the hydrogens sharing a pair of electrons with the oxygen. We've also got what we call lone pairs. Well, they'll be important later on in the next video, but not worried about them at the moment. So 2 hydrogen atoms each share a pair of electrons with an oxygen atom. Okay, now this is a double bond. What's going on here? Well, the 2 carbon atoms are actually sharing 2 pairs of electrons. This is a molecule of ethene, yes, C2H4. The 2 carbon atoms are sharing 2 pairs of electrons, and that's a double bond. Another example of double bonds, carbon dioxide. We know what that is, don't we? And the carbons and the oxygens share 2 pairs of electrons, so you've got 2 double bonds. Going back to ethene, you've got ethane is a single bond, ethene is a double bond, which is 2 pairs of electrons, and then you've got ethyne, which is a triple bond, 3 pairs of electrons. If you're interesting to look at how many hydrogen atoms are involved in each case. Yeah, so single bond, double bond, triple bond. Now, there's a special type of covalent bond that we need to know. If you look at this ammonia molecule, so we've got a nitrogen atom and 3 hydrogen atoms, and the hydrogens are sharing a pair of electrons, and you've got this lone pair. So these 2 electrons at the top, which aren't being used for anything in particular. Now, there's a hydrogen ion. If you put this ammonia in water, then in water there are some hydrogen ions and hydroxide ions as well. Now, what can happen is that the ammonia and the hydrogen ion get together and they form an ammonium ion. Yeah. Now look at what's happening at the top. The hydrogen ion doesn't have any electrons. In fact, a hydrogen ion is just a proton. But you've got a little covalent bond, and where did the electrons come from? Well, they both came from the nitrogen. So notice that in one of the bonds, both of the electrons come from the same atom, and that's called a dative bond, or another name for it is a coordinate bond. Okay? For example, if you dissolve your ammonia in water, then you get ammonium hydroxide. So you get your ammonium ions and some hydroxide OH- ions as well. But that is an ammonium ion. Now, covalent bonds are stronger than ionic bonds, and some covalent bonds are stronger than others. So what does the strength of a covalent bond depend on? And it's pretty logical, really. It depends on the distance between the different nuclei. So if the nuclei are closer together, for example, in the hydrogen molecule, then the positives and the negatives, the strength of attraction between them will be stronger. Yes, so the bond will be stronger. How many pairs of electrons are involved? So a double bond is stronger than a single bond. A triple bond is stronger than a double bond. And you'll notice that it affects the length of the bond as well. And it depends on the electronegativity of the atoms involved. I'm going to do a whole video about electronegativity, but it's basically how attractive the atom is to the electrons in the bond. Some properties of covalent compounds. Covalent compounds are often made up of small molecules, not always. Some of them can be very, very long chains like polymers and enzymes held together with covalent bonds, but often they're made up of small molecules which can be liquids or gases at room temperature. If we look at the gases, nitrogen, oxygen, carbon dioxide, methane, then we've got liquids, some liquids there which are covalent compounds, and then going on to the bigger molecules, we're getting onto sugar, wax, ammonia, and then there are some like polymers and plastics held together with covalent bonds as well. They tend to have low melting and boiling points. Compounds with larger molecules are often solids. The bonds between atoms joined together are very strong, but I'm going to talk in another video about the bonds between the molecules, if there are any, and they tend to be very, very weak. So that's intermolecular forces. So don't confuse. You've got the bonds, which are the actual covalent bonds holding the molecule together, but then you've got molecules perhaps attracting each other. And we get things, for example, hydrogen bonds, but they are intermolecular. So that's a different thing. Some covalent compounds, giant covalent structures. For example, diamond. In diamond, you've got lots and lots and lots of carbon atoms joined together. Lots and lots of tetrahedrons joined together in this giant structure, a large three-dimensional structure held together by strong covalent bonds. Diamond is the hardest natural substance that we know. It's incredibly hard, incredibly difficult to break into bits because it's very, very hard. The whole thing's just lots and lots of covalent bonds. Graphite is also carbon, but that's layers of carbon atoms which can actually slide over each other. Graphite, it's the stuff in your pencil. And when you use a pencil, you're wiping off these layers of carbon atoms. And there's free electrons in between them, which means graphite is actually a good conductor. Another one is silicon dioxide, which is silicon and oxygen atoms. And again, that's tetrahedral as well. Quartz, another name for silicon dioxide. So giant covalent structures is another type of structure that you need to know. Okay, now the next bit, I'm going to waffle on for a couple of slides. Is it important that you understand all of this? It would be nice if you listen to me and read the writing and that kind of makes sense. If it does come up, then there's really only a couple of sentences which you need to regurgitate, because to get into this fully, there's a lot of stuff involved. Let's have a go. Now, we've thought about electrons as being these tiny little particles whizzing around the nucleus. And that's a good way of thinking about electrons, and we can explain a lot about electrons like that. What I'd like you to do now is think about another way of thinking about electrons. Imagine there's a cloud surrounding the nucleus, okay? And this cloud, what it represents is the probability of finding the electron in a particular place. So what we're saying is that in this cloud, like this sphere, on the top diagram, I've chopped it in half. And anywhere in that cloud is where you might find the electron. Looking at it, you won't actually find the electron anywhere near the nucleus. Yes, so you have to move away from the nucleus, and then there is this probability cloud. And the shape of the cloud, you can actually work out the shape of the cloud by thinking of the electron as being like a wave, like a vibrating guitar string, like a standing wave. Now, in this cloud, this sphere, you can actually have two electrons oscillating like two guitar strings, if you like, oscillating in antiphase, opposite to each other. So if you like, when one's going out, the other one's going in, and vice versa. And that's the second diagram. That's my little animation to represent these two electrons oscillating in opposite directions. And this cloud is an orbital. Remember, you can get two electrons in the s orbital, and the s orbitals are shaped like spheres, with one electron, if you like, pulsing outwards and the other electron pulsing inwards. But are they pulsing outwards and inwards? Well, we're getting to the point now where it's getting harder and harder to get a picture in our mind of what's going on. Now, p orbitals aren't spheres. P orbitals are shaped like dumbbells. Yeah, I think it looks to me like two balloons joined together. Okay, so the three p orbitals, remember there are three p orbitals. Yeah, one is in the y direction, one is in the x direction, one is in the z direction. These pairs of balloons joined together. And again, these are clouds, and it's a cloud of probability as to where you might find the electron. Now, in covalent compounds, what happens is that atoms share pairs of electrons, and the clouds overlap. Okay? And there are two ways that they might overlap, that they might merge, and they are called sigma, and you see the Greek letter sigma, and pi. We know the letter pi, don't we? Sigma and pi molecular orbitals. So they are the two ways that the clouds might merge. And so now we're getting on to what you actually need to know. I mean, I do like explaining things. I don't want to chuck stuff at you without explaining it. But basically, the stuff on this slide is what you need to know. In sigma molecular orbitals, the electron clouds are in a line. Yes? The nuclei, the nucleus of each atom is in the middle. It's in the center of the clouds. So you can have two S's, two spheres overlapping. That's an SS overlap. You can have a sphere and a dumbbell overlapping. That's an SP overlap. Or you can have a PP overlap, yes, with the two dumbbells overlapping each other. And they are called sigma molecular orbitals. In a pi molecular orbital, what happens is you've got these two p orbitals, and they merge together and they form two sigma clouds which are side by side. And the two dots in the middle, they're your nuclei. So the nuclei, the line joining the nuclei, isn't actually in the clouds. So P is side by side. Bonds involving sigma orbitals are stronger because there's more overlap and because the electrons are closer to the nucleus. Key points, blimey, we've learnt new stuff today. Key points, so covalent bonds form when atoms join to form molecules by sharing pairs of electrons. One pair is a single bond, two pairs is a double bond, three pairs is a triple bond. Know what a dative bond is, a coordinate bond, and that's where both electrons come from the same atom. Know that the strength of a covalent bond depends on the distance between the nuclei, whether it's a single, double or triple bond, and the electronegativity of the atoms involved. And we'll do electronegativity later, it's dead easy. Some substances have giant molecular structures, for example, diamond. And then we get to this last bit here, and if it comes up in the exam, well, anyway, in sigma molecular orbitals, the nuclei are in a line. Maybe you can sketch a couple of spheres merging together. In pi molecular orbitals, the nuclei are between two sigma clouds. Maybe you can sketch that diagram, yes? And bonds consisting of sigma molecular orbitals are stronger. So if you did understand the last few slides, great, well done. If you just learn those 3 lines at the bottom, if it comes up, I'm sure you'll get most of the marks involved.